Hi guys, let me just let everybody else into the meeting. How you guys doing this morning?
Hey.
Good. All right. So let me, I want to do a quick announcement about what you guys can expect for this week coming up tomorrow for things like homework and stuff. Okay, so this week, so for homework. So for homework, we have chapter 1.3. I know we passed in like the first 5 or so first handful of problems last week. Okay, but this week is the whole of chapter 1.3. Okay, so if you didn't do it last week, do the whole thing. Okay, submit it this week and then go back to last week's and submit. Okay, so I can give you credit on that because that counts as its own homework problem on our gradebook page. So submit it twice if you didn't do it before. So submit it twice so I can give you credit before. So chapter 1.3, chapter 1.4. Also, we're going to do 1.4 today. Okay, so you'll have a chance to do those homework problems tonight, this afternoon, whenever you want to do it. Tomorrow in class, at the end of class, you know, like the last 20 minutes or so, I'll be able to answer questions about 1.4 homeworks. Also, anytime you want to come to office hours and ask questions about it, 1.4 is an awful lot like stuff that we've been doing so far in terms of the derivative, so don't sweat it being a new chapter. Our quiz this week will be on chapter 1.3 and chapter 1.4. Okay, so this is due at midnight, Thursday. You know, I mean, I have a due date on there, but you know how it goes. If you don't complete it, you'll have other options to resubmit it to get those points back. So it's basically due midnight. The quiz will be 1.3, 1.4. Same thing with the availability window like last time, which is the quiz will become available tomorrow afternoon at 12 o'clock, and it'll be available until Friday, okay, at noon. Okay, so then you guys will have 24-hour window in which to take it. But once you start it, you got to complete it. Okay, because it's we have our time limit on there. Okay, on our web page, let's see, so this is available noon Thursday to noon Friday. Okay, and that'll be 30 minutes, just like we did before. By the way, did everybody get a chance to go back into the gradebook and take a look at their quizzes from last week? Because somehow, you know, Canvas, this semester is the first semester we've been using this web hosting platform. So we're still getting used to it, but for some reason, Canvas didn't post the grades once I was done grading them. So I had to go in manually and tell it to post them. You should be able to see not just your grade, but also the comments and stuff that I made on them, like how many points I took off in which spot. So did anybody have a chance to try that out? I had a student in my 8 o'clock class talk about how she did that. I think she was able to go into SpeedGrader and then look at like rubric comments, I think, because when I posted it, it said it was going to post not just the grade, but all the comments on there too. You don't have to do it right now. Go ahead and check it out and then let me know if it doesn't work. Because if it doesn't work, then we got to contact IT and find out what's going on with that. By the way, on our Canvas page, it talked about homework for chapter 1.5 and 1.6. I didn't have a due date on there because I wasn't sure if we were going to get to it this week or not. I'm going to move those until next week. Okay, so I'll also add a due date, which will be next week for 1.5 and 1.6. And I'm going to take those, like the line items for them, I'm going to put them next week. So you'll see them under this week's stuff just for today, and then I'm going to move them around. So just so it won't be as confusing. Okay, so administrative stuff, homework due tomorrow, quiz tomorrow afternoon on these 2 chapter sections here. Okay, and then I have office hours today and tomorrow, so if you guys want to come and ask questions on anything, 1.3 or 1.4, you're free to do that. All right, so let's go ahead and get started. So chapter 1.4, this there's some nuances and details in 1.4 that we didn't cover before, but a lot of the stuff that we are going to talk about in 1.4. We covered actually in 1.2 when we said prelude to the IROC, prelude to the instantaneous rate of change. We were really kind of really getting into it. We're just going to get into it for real. We're going to define it, and we're going to give more details about it today. So 1.4 is the instantaneous rate of change. Okay, this is our IROC. And we're going to call this, we're going to be brave, we're just going to call it for what it is, which is our derivative. Okay, so chapter 1.4. Okay, so this is, I'll put it out formally, definition of the derivative. Okay, so now you're going to want to be tempted when you see exam questions, final exam questions, quiz questions, where they say, you know, do stuff and use the definition of the derivative. You're going to want to be tempted to use things like the power rule, which is going to be very simple. It's a shortcut. Power rule is based on our definition of the derivative. Be super careful, because if it says use the definition of the derivative, and for all problems in chapter 1.4, you must use the definition of the derivative, which is what we've been doing so far. This is our IROC. Okay, so this is our IROC of our function f of x with respect to x at the point x equals a. So we're now specifically looking at our derivative at a specific x value. So we say f prime of a, our derivative at a, equals the limit as delta x approaches, or we're going to talk about what these things are, f of a plus delta x minus f of a all over delta x. We've been calling delta x h, right? So we'll just write it out like that again. So limit h goes to 0, f of a plus h minus f of a all over h. This is our definition of the derivative. It's a limit process, right? This is why we spend so much time on limits, because it forms the foundation for all the stuff that we're going to be doing, not just in calculus, but in like basically all of your engineering classes going forward. Limits are such an important piece, okay? So here's our definition of the derivative. It's a limit process. If the limit exists, then my derivative will exist. So this will put that caveat, so provided limit exists. And now we know, right, the criteria under which a limit will exist or on which it won't exist. Okay, so that's why we spend so much time on it. Okay, so let's remember our secant line. Right, our secant line was our average rate of change, right? So let's draw out this picture. And like, why are we doing this stuff? I've got my axis, I've got my y-axis, I've got my x-axis, comes down. Now I've got this function, my function's doing something, right? So this is my f of x, okay? And then what's gonna be happening is I'm looking at a particular value, right? X equals a. I wanna find out what's my function doing at x equals a. So you can see my function's got all these curves, right? It's like, if I look at my linear function, y equals mx plus b, my slope is really obvious. I can yank it. I can look at my graph. It's just a straight line. I can yank it right out of the equation. I can see what's the rate of change of this linear equation. Something like more complex, anything more complex than a linear equation, my rate of change is going to be changing at every instance of x, right? It has the potential to change at every instance of x. So I need a tool to tell me what's the rate of change when x equals a, when x equals a plus 1, when x equals a plus 2, so on and so forth. I need to know how is this function changing as x changes, right? So I do this with my secant line. So that's right, I've got my point P, okay? And say I've got some other point Q, okay? And I go to draw a secant line. So let's draw, I'll draw the secant line in green. So here's our secant line. Okay, now remember our secant line, it's a straight line, like y equals mx plus b, straight line, and it goes through 2 points on f of x, right? And this is our p and q. It's going through 2 points on f of x, right? And so let's make this down. This is some, a plus h value, right? We've got some a plus h value. Now remember, if I make h as h goes to 0, as I decrease that distance, right, between where I want to look, I want to know what's the function doing at x equals a, but I've got this secant line. Now I'm going to reduce this, right? I'm going to make my h a little bit smaller, and I'm going to draw another secant line. Here's another secant line. Notice how I didn't change p. P is where I want to focus what's actually happening. Now I'm going to change, I'm going to make h a little bit smaller. So as h goes to 0, right, I'm going to make h a little bit smaller. I'm going to make another, as h gets even a little bit smaller. Here's another secant line. Here's another one. Here's another secant line. As h gets smaller and smaller, as h gets smaller and smaller. So you see all these secant lines, right? This is our limit process. Now watch what happens. I'm going to put a dot here. So the red line is our tangent line, right? Our tangent line touches our function at only one point. This would be our x equals a point, okay? So x equals a, f of a, so this right here, right? That's the point that we're looking at. Now, if I take the slope of my tangent line at x equals a, the slope of my tangent line tells me the rate of change of my function f of x when x is equal to a, okay? Now, we did all this stuff with the secant lines, right? So as h gets smaller and smaller and smaller and smaller, I'm approaching, my secant lines are approaching my tangent line. That's our limit process. That's what we do right here. This is our secant line. I make h a little bit smaller, I take it again. I make h a little bit smaller, I take it again, I take it again. The whole point is to get to our tangent line, okay? So now I can say the limit as h goes to 0, f of x minus f of a all over x minus a is equal to f prime of a, okay? This right here, this is our slope of the tangent line. The derivative of our function at x equals a is the slope of our tangent line. That's what we're doing right here, okay? That tells me the rate of change, the instantaneous rate of change at that instant x equals a, okay? But I have to do this whole, my secant lines are getting closer and closer until they're basically equal to my tangent line, right? The age difference is so infinitesimally small, it's essentially equal to 0. That's the whole point of the limit, okay? So graphically, definition-wise, okay? That process that we've been doing so far. Give you guys a minute to finish writing that down, and then I'm going to turn the page. Okay, so let's come up with, we'll define our tangent line for real. Okay, so our tangent line. Okay, our tangent line. So first off, we're going to assume our function is differentiable at x equals a. That's what we're looking at. Okay, so assuming it's differentiable, it means which means it's continuous at x equals a. Okay, so the tangent line to the graph y equals f of x at p. That's our point P, which is a, f of a, right? So this was our x equals a. I plug it into my function and I get a y coordinate. My xy coordinate is that P that we had in our graph. So this is the line through P, which has a slope f prime of a. So the slope of our tangent line, okay, at this particular point, I have a point and I have a slope. I can plunk it in, I can get the equation. you'll be asked for the equation of the tangent line. I'm going to leave it in point slope form. Don't worry about giving it to me in y equals mx plus b form. Point slope form is your easiest bet. Okay, so I'm going to go y minus f of a equals f prime of a x minus a. Let's make notes, right? So this is our slope. This right here is our y coordinate of our point. This here is our x coordinate of our point. Okay, so this is the slope. That's the slope of our tangent line that we found with our limit process right there. Okay, we're going to go through some examples so you can see how this works. I've got my lecture examples for chapter 1.4. I'm going to pull those out. You're free to use those or not. Remember, every day that I complete one of these, right, I scan it in and post it right underneath where the lecture examples are originally posted. So 1.3 was posted on Monday, but it's in last week's because that's where 1.3 was originally posted for lecture examples. So 1.4 I'll post today. So let's do lecture example number 1 for 1.4. So we want to find the equation of the tangent line to the graph, y equals x squared. So this is our parabola, right? And at x equals 5, right? So I want to be able to find, I expect my tangent line is going to look like this. I'm not finding this very well here. There's our tangent line. Okay, so I want to find the equation for that. All right, so I need to do a couple things. So I have to compute slope, which means I'm doing f prime of 5. Okay, this is our a value, right? A equals 5. So f prime of 5 equals the limit as x approaches 5 of f of x minus f of 5 all over x minus 5. Okay, so I've got my function f of x, and wherever I see an x in my function, I plug in 5. So this is what I'm going to be filling in the blanks with. So this is going to be the limit. Don't forget it's a limit process as x approaches 5 of my function x squared minus x squared at 5. 5 squared all over x minus 5. Okay, I can't do direct substitution immediately because I'll get a divide by 0 error. So I've got to clean it up. This is our removable discontinuity. So the limit as x approaches 5, I'm going to factor out the numerator. X plus 5, x minus 5, x minus 5. Right, I can do this removable discontinuity here. So this is going to give me the limit as x goes to 5 of x plus 5, which is equal to 10. Okay, that's the slope of our tangent line. So slope of tangent line equals 10. It's a positive number, right? Let's just do a quick reality check. I'm looking at the graph. At x equals 5, my tangent line has a positive slope algebraically. And look, it's an upward sloping graph, which means this has a positive slope. The graph and your algebra should line up. Okay, if they don't, maybe you've made a mistake in one place or another. But we don't grade you on the graph. So go ahead and take a look at the graph. It should help you kind of get a ballpark. Like, are you doing this right? Okay, so my next step is find the equation for a tangent line. Okay, so for the equation of the tangent line, I need a point. Right, so I'm told I've got x equals 5. So what's f of 5? I plug in, I'm going to get 5 squared, which is 25. So the point, my xy point is 5, comma 25. Okay, I have a point, I've got the slope. I'm going to use point slope form. So y minus 25 equals 10 times x minus 5. Leave it like that. Please don't convert that into y equals mx plus b form unless you are told specifically slope-intercept form. Then you can go ahead and convert it. Otherwise, if you're not told, or if you're told to leave it in point slope form, just leave it. Okay, don't worry about cleaning it up. This is how it's supposed to look. Okay, so this is the equation of our tangent line right here. Okay. All right, let's try our next example. Sketch the graph of y f of x equals 1 over x. We want to find the tangent line at x equals 2. Here's x, here's y. I know this rational function here has an asymptote at x equals 0 and y equals 0. So I'm going to just kind of plot them there. And this rational function looks like this. And it looks like that. You can graph this out on your calculator too. And then this is what it will look like. So x equals 2 right here. So my tangent line is going to be like this. Okay, kind of what I'm expecting. So, right, I don't have a discontinuity on my function at x equals 2. If I was told to find the equation for the tangent line at x equals 0, I wouldn't be able to do it because the function has a discontinuity at x equals 0, which means it's not differentiable at x equals 0. So I wouldn't be able, there is no tangent line at x equals 0. X equals 2, totally fine, right? All right, so let's go ahead and do it. So we have to compute the slope at x equals 2. All right, so we're going to do that. This is our definition of the derivative, which is our limit process. So I'm going to say f prime of 2 equals the limit as x approaches 2 of x minus f of 2 all over x minus 2, which is equal to the limit as x goes to 2 of, now I'm going to plug into my function, 1 over x minus 1 over 2, right? So I plug in x equals 2 into my function, all over x minus 2. Now I have to clean this up. If I just do direct substitution on my limit, I'll get a divide by 0. So I have to find a common denominator on my numerator, which means I have to multiply this side by 2, this side by x, combine them across the top. Forget we're still taking the limit of everything. And that's going to give me 2 minus x all over 2 times x all over x minus 2. And remember, this is a fraction. It's over 1, which means I can multiply by the reciprocal top and bottom. So I'm going to get the limit, x goes to 2 of 2 minus x all over 2x times x minus 2. So close, right? I can factor out a negative 1 on my numerator. Just going to look like, I'll put it over here, limit as x goes to 2 of, I'm going to factor out a negative 1. Put it in the wrong spot. Then I'm going to get x minus 2 all over 2x, x minus 2. Which means I've got this removable discontinuity. I can get rid of that. So that means I'm going to get the limit as x goes to 2 of minus 1 all over 2x. Now I can do substitution. And I get the limit is equal to minus 1 over 2 times 2, minus 1 over 4. That's the slope of my tangent line, which makes sense, right? Look, my tangent line is downward facing. It should have a negative slope. I expect it to, I think, and it does. Algebraically speaking, I get a negative slope. Okay, these things should line up. Okay, so now I need the equation. Okay, so for the equation of the tangent line, I need a point on the line. We were told to look at x equals 2. So x equals 2, f of 2 equals, I'm just going to plug it in, 1/2. Okay, so my point is equal to 2 comma 1/2. I'm going to do point slope form because I could just plunk it right down in there. So y minus 1/2 equals my slope minus 1/4 times x minus 2. And then I'm done. That's the equation for my tangent line at x equals 2. That describes this red line right here. Okay. Questions so far? Give you guys a second to finish writing that. Okay. All right. So let's talk about notations or derivative as a function. Okay, so what is this going to look like? We've done the prime, so f prime. I say y equals f of x. I can then say y prime. I can say dy dx. So change in y over change in x, y. Or if I have an f of x, so df dx. This bottom part is important because it says with respect to which variable. This becomes more important, especially as we go on to more complex functions or have multiple variables. I need to know exactly which variable I'm taking the derivative of with respect to. I can do it at a particular point, right? So it's going to look like that. y prime of a. This is a little bit cumbersome. We usually typically say f prime of a like we did in our previous examples. I can also say something like dy dx evaluated at x equals a. Okay, same thing as this. Or I can say dy dx and then just say a, right? It's assumed x equals a. Okay. I can go df dx equals a, or df dx evaluated at x equals a. All of these things are the same. Okay, same notation. If the function gets kind of complex, I can go dx of x, whatever that function is. It means take the derivative with respect to x of this function, whatever it is. Okay, the thing that we want to keep in mind is dy dx is equal to the limit as delta x goes to 0, the change in y over the change in x. This is our secant line, right? So this right here, this is not a fraction. This is like a process. We're defining a function. This is like the label of a computer program. This is what we're going to do. And this here, right here, this is a limit of a fraction. Right? This is our slope of our secant line, and we're approaching our tangent line. So this is a limit of a fraction. But this right here isn't a fraction. Okay? And that's important because you want to be careful. You don't want to jump in and cancel things out because it's really just telling you what kind of function you're going to be doing. So that's notation. I still have that. Okay. So you write it out specifically. So I'm going to write derivative as a function. Okay, so I'll say f prime of x equals the limit as h goes to 0, f of x plus h minus x all over h. This is our definition of the derivative, right? So we say f of x is differentiable on some interval a to b if our derivative exists, which means that our limit, right? So if this limit doesn't exist, then my derivative doesn't exist, which means my function isn't differentiable. Okay, that becomes important. We're using our limits to talk about continuity, essentially, right? If I have continuity on the function, right, then I can talk about derivatives. Okay. Also, we have what's called a constant. I'm going to throw out some rules that are going to make our derivatives easier. So constant multiplier rule says if I've got this derivative I'm trying to do, d dx of some c, some constant times my function. So c is a constant. And what I can do is I can pull out that constant and I can take the derivative of my function and then multiply by the constant later. We've actually been doing this. If you've been calc before and you've done the power rule, right, and it had like, you know, a coefficient on some term, this is, you use the constant multiplier rule. So let's also talk about a couple other rules. So I'm throwing out some rules here that we're actually going to show why this is true later in a later chapter, but we need these shortcuts, simplifications, so that we can give examples that are more complex. Our book does this a lot, right? It uses things before it actually, you know, explains what it is. So bear with me here. This is kind of how our book is setting up. So we say c is some constant, you know, some number. One of the things that happens is if I take a derivative of a constant, it's equal to 0. We'll talk about why that is in a later chapter. Another rule is if I have just plain old x to the 1, and I take its derivative, like its exponent is equal to 1. The derivative of x is just equal to 1. We'll talk about why it is later. We need these so we can do some more complex problems now. If I take the derivative of x squared, I'm going to get 2x. Okay. Like I said, these are essentially the power rule that we're using right now, but our book likes to give us things before we've actually explained what they are, so we can use them even though we officially don't know what the power rule is. Okay. With that, I'm taking out my lecture examples and I'm looking at Lecture example number 3, we're going to use some of this stuff in lecture example number 3. So number 3 example says, prove that x to the minus 2 is differentiable and calculate our derivative y prime. So first off, I'm going to rewrite this. Y equals x to the minus 2. I'm going to write that as 1 over x squared, right? Every time I see a negative exponent, that means that value needs to be on the other side of my dividing line. When I see it like this, it becomes more obvious to me that I have a domain restriction that I have to know. I have a domain restriction. X can't be equal to 0, right? So whenever we find our derivative, we have to include this domain restriction because our function, right? I think this function looks like this. It's got an asymptote, a vertical asymptote at x equals 0. All right, so let's go ahead and jump in. So y prime. We're going to look at our derivative. We need to use the definition of the derivative. Don't be tempted to use the power rule unless you're kind of open. You're told that you can use it. At this point, we officially haven't learned the power rule, so everything that we do is definition of the derivative. Okay, so y prime is equal to our limit as h goes to 0, f of x plus h minus f of x, it's a minus all over h. Whenever I do these problems, I always write out what my function is that I'm going to be doing first, right? Limit h goes to 0, f of x plus h minus f of x all over h. It helps me remember all the things I have to plug in and all the things I have to do. Plus, it reminds me it's a limit process that I'm doing. If you do this first and you forget to do the limit until the very end, I can grade you correctly because you have a limit here and you have a limit at the end, you're evaluating it. If you forget this part and you forget the limit until you put the limit at the very end and then you evaluate it, I have to take off points because this is a limit process. Also, if you forget the limit altogether, I have to take off points because this whole thing is a limit process. So don't forget this limit part. Okay, so let's plug things in. So this looks like the limit as h goes to 0. F of x plus h. So everywhere I see an x, I plug in an x plus h. 1 over x plus h quantity squared minus 1 over, that's our function, all over h. Okay, so again, I need to find a common denominator. Okay, so common denominator, right? What I'm going to do is I'm going to bring up the h into that. I'm going to combine those terms, and then let's see, we'll bring up the h in a minute. So common denominator. So what that means is I'm not going to worry about, please, whatever you do, don't FOIL this out and then try to find a common denominator that way. Your common denominator is just this h squared. Leave it as a block. Okay, so I'm just going to multiply through and I'm going to combine. So this is going to be limit h goes to 0. This is going to be x squared minus x plus h quantity squared all over x squared, x plus h quantity squared all over h. I'm going to write h over 1. Okay, I'm going to multiply, right? There's a couple steps that I'm going to do here that I'm going to simplify out. I'm not going to I'll show you. So what I'm going to do is I'm going to FOIL this out. FOIL, combine like terms, right? Which means I'm going to be able to cancel some things out, right? And then I'm going to multiply by reciprocal, whoops, of denominator, 1 over h, which brings the h up into that fraction there. So this is going to look like the limit as h goes to 0. This is x squared minus 2xh minus h squared, right? I multiplied this out, but I had to distribute the negative to all of those terms. So be very careful. Don't lose track of your negatives. Okay, all over, this is multiplied by the reciprocal, x squared, x plus h quantity squared. Okay, what I'm going to do is I'm going to combine terms, combine like terms here, which means I'm going to be able to cancel out some of these like terms. I'm going to factor h out of numerator and then cancel with h in denominator. And it's going to look like this. So the limit as h goes to 0, right? So I factor out, I'm going to get minus 2x minus h all over x squared, x squared times x plus h quantity squared. Now I get to evaluate the limit by substitution. Okay, so I'm going to plug it in. Substitution, h goes to 0. It's not going to be a problem this time. So I'm going to get minus 2x all over x to the fourth. Be careful. Substitution means x squared times, this is x plus 0 quantity squared. X squared times x squared gives me x to the fourth. I can clean these up. I'm going to get minus 2 all over x cubed. This is equal to my y prime, my derivative. Okay, so what we say we're going to conclude is that the limit exists for all x not equal to 0, because I have a domain restriction there. So y is differentiable. Differentiable everywhere except this domain restriction, x not equal to 0. Okay. All right, so just put our notes, our algebra notes in a different color there so you can see. Give you guys a minute to finish writing that. You guys all set? Right. So another rule that we're going to talk about is the linearity. This is a definition. Oops, linearity rule. Okay, so we're coming up with a definition for this here. So we're going to assume we've got these two functions, f of x and g of x are differentiable. Individually speaking, f is differentiable, g is differentiable. That means if these individually are differentiable, then f of x plus or minus g of x is also differentiable. If you've been doing calculus before and you were given, like, you know, quadratic equation, x squared plus 2x plus 1, for example, and you're told to take the derivative of that. X squared is my f of x, 2x is my g of x. I actually have a third function, h of x, which is my constant term, right? And I take the derivative of each one and I add or subtract them all together. That's exactly what we're doing here. It's our linearity rule. Linearity applies to addition and subtraction. We have different rules for multiplication and division. So keep that in mind. Linearity, addition, and subtraction. So I can also write this as f plus or minus g prime of x. These are just different ways of notating it. And that's equal to f prime of x plus or minus g prime of x. Right, so if I add, I'm going to add. If I subtract, I'm going to subtract. Okay, which is also, I can also write this as oops, f of x plus or minus g of x prime. Okay, these are all equivalent statements, okay? Or I can write it as dx, right, of f plus g, f plus or minus g. That's equal to df dx plus dg dx. These are all just different ways of notating the same thing, our linearity rule. Okay. Right, I'm taking a look at my next example, example 4. Okay, so example 4 says, find the points on the graph. We've got our function t cubed minus 12t minus 4 where the tangent line is horizontal. I'm just gonna, like I say, I always like to do a quick sketch. Right, you're not graded on these sketches, so, you know, go ahead and plot it out if you want. So where the tangent line is horizontal, so let's talk about like what that means. Tangent line is horizontal, right? That's like basically looking at, it means that our tangent line has slope equal to 0. So when I have a slope equal to 0, it's completely horizontal, right? Y equals 0, 0 times x. So y equals mx plus b, y equals mx, m equals 0. My slope is equal to 0. So we're looking at someplace like here. It looks like we're going to find out it's here. It's here. So our tangent line is going to be horizontal at these different points. So you need to figure out what these points are. I want to find out what that is. Okay. So there's a lot going on in this this problem here. There's a lot of great things. We're going to be actually exploring this whole idea in quite a bit of detail in chapter 1.5 and then going forward. All right, but let's go ahead and start off with what we know. So df dx. Okay, so what I'm going to do is, I'm sorry, dt. So dt of t cubed minus 12t minus 4. Okay. So now I'm going to break my linearity rule. Says I can do this. I can say d dt of t cubed minus d dt of 12t minus d dt of 4. Okay, I'm really breaking this down into component pieces to show you all these nitty-gritty steps. You know, ultimately, when we get to things like the power rule, this is going to be a very straightforward derivative to find, but it's all based on these individual rules. Okay, so that's why we're spending a lot of time doing all the nitty-gritty details on it now. Okay, so remember, we gave you some shortcuts for these. So the derivative of a constant was equal to 0. The derivative of t was equal to 1 times our constant multiplier here. So this is just equal to minus 12 minus 0. This part here, I'm going to go use my definition of the derivative. Okay, which is our limit process. So remember, we officially haven't learned our power rule yet. Okay, so the limit as h goes to 0 of t plus h cubed minus t cubed over h. Okay, so here I need to expand this polynomial here, and then it's going to look like the limit as h goes to 0 of t cubed plus 3t squared h plus 3t squared plus h cubed minus t cubed. I don't care how you, if you want to FOIL out and distribute all these terms, if you want to use the polynomial expansion, Pascal's triangle, fine. Either way, just make sure you do it correctly, all over h. Okay, so we're going to combine like terms, which means I can cancel out some of these things. I can factor out an h term and I can cancel it off with here. Okay, so when I do that, h goes to 0, I'm going to get 3t squared plus 3th plus h squared. And when I evaluate my limit using substitution, I'm going to get 3t squared. This right here is just that derivative for that piece right there. So I'm going to put it all together. This is our linearity. Right, so our derivative, f t equals 3t squared, our first piece, minus 12 minus 0. I'm not going to remember about the minus 0 part. So that's our derivative, f prime of t. So they said, that's our first part of what we're trying to do. They said, now where is this thing, you know, equal to 0? Where's the slope equal to 0? So I'm going to ask that question. So where is f prime of t equal to 0? At what t value is this going to be equal to 0? So I take this, 3t squared minus 12, and I set it equal to 0, and I solve for t. So this would work like in a velocity as a function of time. We'd say at what time is the velocity equal to 0, right? And we would solve for t. So now I'm going to do this. So I'm going to say 3t squared equals 12, divide by 3, squared equals 4. I take the square root of both sides. So t equals, watch what happens when I take the square root. I have two roots, right? A positive and a negative. So t equals positive 2, t equals negative 2 are going to be the two different t's where my slope of my tangent line is horizontal. Okay. Horizontal at t equals 2 and t equals minus 2. Okay. So I'm going to scroll up here. So right here, so t equals minus 2 and then t equals positive 2. Okay. So that's where my tangent line was horizontal, where my slope of my tangent line was equal to 0. I had to go through and do all that derivative, find these t values here. Okay. I know it's cumbersome. You just want to jump right to the power rule and do it. Power rule is going to help you in your mind before we learn it. It's going to help you in your mind to know that you've done the definition of the derivative correctly, but be very careful. Especially the problems are going to tell you, all the 1.4 problems you're going to be assuming to use the power rule. It's going to be cumbersome and tedious, but you've got to work, I'm sorry, not the definition of the derivative in 1.4. It's cumbersome and tedious, but that's actually where our power rule comes from. Okay, it's a shortcut to this definition of the derivative. So be very careful, don't skip it when you're doing 1.4 problems. So I've got a couple of theorems to talk about, and then we'll do one last example on 1.4. So our first theorem, so we say if our function f of x is differentiable at x some value, then f, the function, is continuous at x, right? Because our derivative is a limit process. We use the limits to help us discuss continuity. If I can take a derivative, it means, and I can get a derivative, my limit exists, which means that my function is continuous, and vice versa. Which means if our function is continuous at x, then our function is also differentiable at x. Okay, it's a really important idea, right? Continuity and differentiability go hand in hand because they're both limit processes, which is why we spend so much time on limits, so that we make sure we have that. Okay, the other theorem, it's more like a, want to just kind of give it to you. Our derivative of, let's say I've got the function f of x equals e to the x. E to the x is an exponential function, right, with the base e. So we're going to talk about specifics. So if I take the derivative, it's a really important function because it's equal to its own derivative. Super important. Okay, I'm going to generalize to any exponential function. Right, so base b. So base e is our exponential function, so base b. So we say f of x equals b to the x, right? In this case, b was equal to e. E is our transcendental number, 2.718, so on and so forth, right? So, but I could have a base b equal to anything, right? So I want to take this derivative, right? Same as we did before, I repeat the function. I take the natural log of my base, right? So this is going to be a number, natural log of my base. And then we'll find out later, this is our chain rule, dx. I have to take the derivative of what's up here. Most cases, like for this case, it'll just be equal to 1, but I need to put that in there for now. This part's important, right? Don't forget the natural log of our base. We're doing it here too, we just don't see it because the natural log of e is equal to 1. Okay, so it's here, but it's invisible. Okay. General exponential, specific exponential. We're going to use this way more often than this one, but it's good to know what the derivative is of a general exponential function. All right, here's our last example. So example 5 says we've got this function absolute value of x. So I'm just going to plot that out. Right. My absolute value of x is like this. So I've got this point right here, right? We want to show that this function's not continuous and at x equals 0, and it's not so it's not continuous and therefore not differentiable at x equals 0. We want to be able to show that, right? It looks like it should be, but this is what we call a cusp. It's a very specific point there. So let's take a look. So my f of x is equal to absolute value of x, which means when x is greater than or equal to 0, my absolute value of x is equal to x. If x is less than or equal to 0, my absolute value of x is equal to negative x. I've included the equality on both of those because 0 equals negative 0. It's the same number. The absolute value of 0 is equal to 0. Okay, so if I take the one-sided limit, one-sided limits, right? So what's going to happen is I'm going to do things at x equals 0, right? Because we're looking at x is equal to 0 here. So I'm going to be looking at f of 0 plus h minus f of 0 all over h. So how this ends up is it looks like absolute value of h all over h, right? This is our function, okay? So if I take the one-sided limits, it looks like this. Let's see, limit as h goes to 0 from the left-hand side. Absolute value of h all over h. This is equal to the limit as h goes to 0 from the left of minus h all over h, which is equal to minus 1. Okay, my right-hand side limit as h goes to 0 from the right-hand side of my function equals limit goes to 0 from the right-hand side. It's positive h all over h, because remember we specified that at the beginning. positive one. Remember we said about limits, our left and our right-hand limits don't agree. Are not equal to each other. Okay, if the limits are not equal to each other, therefore it's not continuous at x equals 0. It's not continuous at x equals 0. If it's not continuous at x equals 0, therefore it's not differentiable at x equals 0. Okay, so we're using the idea of continuity, right, to talk about differentiability, okay, because they're both based on the limit process here. You guys finish writing that. That's the end of 1.4. We have about 10 minutes, so I'd like to actually start on 1.5. We're going to get a little bit into 1.5, and then we'll continue 1.5 tomorrow. You guys all set with this? I'll scan this in later today, and I'll put it up on our Canvas page, right underneath where I posted the blank page of the lecture examples. Chapter 1.5 starts getting into the details of our derivative, and we start getting into using the derivative to talk about our function doing interesting things. So 1.5 is, we're talking about extreme values of our function, and the mean value theorem. We're going to talk about extrema today and the mean value theorem later. Okay, so sort of what are we talking about when we talk about extrema? So this is going to refer to maximum, minimum values. We're going to refer to them as extreme values or extrema. Okay, we can also call these things like local maxima. You may have heard these before: local maxima, local minima. We're going to define all these things in this chapter section. So the process of finding these values is called optimization. It's super important, right? We want to be able to find these, you know, maximum, minimum, local max, local min values. We're going to talk all about that, but that's optimization, right? Because interesting things are happening at these places. Okay, so let's actually come up with, this is sort of like paraphrasing. Let's come up with a more formal definition in math. So definition. So we're going to talk about extreme values, so max and min, on an interval I. Okay, so extreme values along some interval. So let's say we're going to let our function, let f of x be a function on this interval I. Okay, so I've got some functions doing something like func it. I've got some interval from a to b. Okay, now a and b could be minus infinity to positive infinity. We'll see, like, we're going to make it finite. We're going to look on some interval. Okay, I'm going to evaluate my function along this interval here. We're going to talk all about closed intervals, open intervals, all that kind of stuff. But for now, we're just thinking about our function within this interval. And we're going to let some value of x equals a, be what we call an element of that interval. So I break up, my interval goes from a to b, right? And then I've got some value within this interval that's part of that interval. This is my x interval. Okay, so I'm writing this in math, but I'm trying to translate it so you know what it means. So we say that my function evaluated at a is the one of the above absolute minimum. So it's the absolute minimum along this interval of our function if we say f of a is less than or equal to f of x for all values along that interval. right? So I break up my interval into x values, right? X goes from A to B. My minimum, it's an absolute minimum along this interval if that function value evaluated at A is the smallest value for all values along that. Likewise, for the maximum, we say that f of A is an absolute maximum f of x if this is on our interval, if f of A is greater than or equal to f of x for all x element of I. So we're writing it in math, but we're trying to translate it into English so you know, right? So this is our biggest function value, or largest function value along this interval. Okay, that makes it our absolute maximum. So extreme values along some interval. Now, keep in mind, there are exceptions, right? So let's talk about some of those exceptions. So not every function will have a maximum or minimum, right? It's going to happen, right? I mean, my functions, there's a whole bunch. So think about, for example, f of x equals x, y equals x. Nice linear function, right? It looks like this, like that, okay? Look what's happening, right? My function increases without bound as x goes off to positive infinity, right? Whoop. My function keeps getting bigger as x gets bigger. There's no maximum value because everything is just, you know, continues to be the maximum. Likewise, in the opposite direction, f of x decreases without bound as x approaches negative infinity, right? We're going in this direction here. Right, so I don't have a maximum or a minimum on this particular function. So there are exceptions, right? No matter what. It's also possible I can have a discontinuity that's gonna throw a monkey wrench into stuff. Let's see, let me draw out an example of what that would look like. A solid line here. So watch what's happening here. These should be straight lines. My function is approaching, right? As I approach C, my function is approaching 3 on either side. But at x equals C, my function is equal to 2. Okay, so my function is actually not defined at x equals C. Like the limit and the function value are different at x equals C. That makes it, I'm sorry, it's defined, but it's a discontinuity, right? So this has a discontinuity, right? We expect, like if this was defined here, we would say that that would be our maximum. So there's no maximum on here, okay? So our function has a discontinuity and no maximum value. No maximum value, right? Because look, it should be, this should be our maximum value. F of C equals 3 should be our maximum value because our limit, it's approaching 3, but it's not equal to 3, it's equal to 2. So it has no maximum value. The values of our function get close to 3 from the left and the right, from, you know, from, as we go up from below it, but 3 is not maximum because our function does not take on that value, right? It's not equal to that value. The function takes on the value. And where it should be 3, it's equal to 2, right? I mean, the limit points to 3, but the function's defined it 2. Okay, so we have a discontinuity here. So we've got some things that are going to throw like a monkey wrench in our business, okay? But it's fine either way. We're just going to define what these things are and then work around them. Okay, so what I'm going to do is I'm going to leave you guys with this on chapter 1.5. Tomorrow we'll pick up with the rest of 1.5, okay? And we'll work it from there. At the end of class tomorrow, I'll answer questions on homework for 1.4. Okay, you're welcome to come to office hours today and tomorrow to ask about any of the homeworks, 1.3 or 1.4 or any of the earlier stuff. And I can answer questions on that at that point. Okay. Otherwise, you guys have a great day.
Thank you.
Bye.
Okay, take it easy.
Thank
Take
you.
care.